Hello everyone, let's talk about biasing of transistor. If you see schematic of transistor, you would see something like this. Now, biasing generally means to add a specific amount of DC voltage so that it can uh, overcome the potential barrier of this base to emitter terminal, and because of that the input signal, even though how much less it is, it can flow through the circuit and produce amplification. This is what the transistor is used for. Now, as I said, this is a base terminal, this is the emitter terminal, and this is collector terminal. The operation of the transistor is in such a way that when a small voltage is allowed to pass through this BE, this BE path, then a large amount of current would flow from collector to emitter terminal. So this is what the operation of a typical transistor look like. Now, if I say the biasing of a transistor means to add specific amount of DC voltage so that the operation of the transistor is 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 available, or such that the transistor works. Now, there are a lot of reasons to this biasing, and one of the reason of them is to operate this transistor in operating line. That means to bring the operating point of this transistor, operating point of this transistor in the middle of operating line, such that there is minimum distortion. Now, what does that mean? That means that if we have a AC signal which looks like this, and if we have a lower boundary, or the lower boundary, then these amount of signals are cut. That means this amount of signals are lost. That means a significant part of the signals are lost if the operating point does not lie in the middle of the line. And if we do this biasing, it somehow becomes the case where operating line operating point lies in the middle of the load line, and as a result of which the input signal is not lost. That means the limits or the boundaries becomes maximum enough to let all this input signal pass through the transistor. So this is what the main one of the reasons why biasing of a transistor is done. Okay, now let's talk about, now there are a lot of ways to do biasing of a transistor. Let's see all of them one by one. This circuit you see here is a common emitter circuit. Now, to bias this by using something called base bias, what you do is you provide a specific amount of resistance, something called RB resistance at the base terminal, and a specific amount of voltage. A specific amount of voltage at this node, which is called VBB, and similarly provide a resistance at the collector terminal and a specific amount of voltage, which is called VCC, and this is what the base bias looks like. Okay, what you did is you provided or you added some specific amount of resistance and voltages, and this is it. This is what did base biasing of VCE circuit. Okay, now this circuit can be drawn equivalently by using AC analysis also. Now, if you want to draw this circuit and perform AC analysis, we must firstly form or AC equivalent circuit of this. Then that would help us to do a lot of calculations and AC analysis. And for that, uh, the equivalent circuit of this would look like this. So what you do here is you replace this transistor by using a diode. The first thing you would like to do is replace for equivalent circuit. What you do is replace transistor with the diode, and it looks like this. This is a biasing voltage VBB, and we have some resistance, and we have a diode which is forward bias, and at this same ground terminal we use AC input. Again another biasing voltage VCC, and this is what the equivalent circuit looks like. Okay, so this is what the equivalent circuit looks like. Now if you want to find out the current of the circuit, then the first current that you would like to know is current through this base terminal, that is IB. And if you now IB here is equals to VB minus the voltage at this terminal, right? So voltage at this terminal, that is VBE by RB. So this is what we get for this expression for base current. Now if you want to know what the collector current is, you know in the transistor it's just beta times IB. This is what we get for the expression of IC. Now what about this voltage VC? What is the amount of VCE? To know this, you would like to perform Kirchhoff analysis, and if you do so, it's VCE, which is this, is equals to VCC minus the current that goes from this resistance, the voltage drop after this resistance, that is given by this formula. Now if you apply the value of this and here, then you would get something like this, which is VCC minus IC is beta times IB, that means beta times VBB minus VBE by RB. So this is the expression for the voltage that goes from collector to emitter terminal. Okay, so after finding this, you can also find out the value of IC from here, and you can express it in terms of IB by this expression, by equating it. Okay, I think you understand that. So let's move on. And okay, so if you do that, for example, okay, I would like to do that. Just wait for a while. Yes. So if you want to find an expression of IC, that would be, and if you remember this expression, it looks something like this, right? Where C minus VCC by RC and X, sorry, and M is 1 by RC, right? So if you do so, or if you express this in this way, then you would get something like something. Okay, so if you want this, this is a straight line linear equation, and if you express it in graph, it looks something like this, and this y terminal represent this, which is IC, and the x is VCE, so it's VCE, right? It's VCE, and the slope here, which is given by the value 1 by RC, is this, and this is the y-intercept, minus VCC by RC. So this is how we get the operating point. Sorry, this is a slope, right? Now, if you now somewhere in this graph there lies something called operating point that we were talking about. We would do a detailed analysis of it in just a bit, but let's grasp for now. Let's grasp this concept only. So I think you understand what's going on here. Okay, so this is it. Okay, this is it. Now, because of that, you'd find something called saturation current and saturation voltage, and that means when VCC, oh sorry, now what do you mean by saturation? Saturation means when this VCE is 0, right? Now when it is 0, then if we apply VCE equals 0 in every expression, I would get IC equals minus VCC by RC, and this is saturation collector current. Similarly, if I apply VBE equals 0, then IB saturated will be VBB by RB. In this way, we can find out the values of saturation current of collector current and saturated voltage current, sorry, base current. So this is it. This is all about base bias. Okay, now let's talk about voltage divider bias. This is what we call as a voltage divider bias, and if you see this, the voltage divider, the name itself is clear because of the fact that this VCC voltage is divided in between this R1 and R2 before going to this base terminal on the basis of the ratio of these resistances. So this is a this is a emitter resistance which is connected to the ground, and this is a collector resistance which directly added or connected to the a voltage source. Now this is a very popular biasing system or mechanism because it helps us to find out, to find out the operating point, or to let that operating point to be in the middle of the load line, as a result of which the cutoff as well as saturation would not have any impact on the operating point. That means there is little as little edge as little distortion as possible uh, uh, by using this voltage divided bias, and that is one of the reason of its popularity too, uh, because the distortion of the input signal is very less in this kind of biasing. Now let's talk about now one of the and another thing about this voltage divided bias is that it does not depend on beta. Now you know that this beta is actually dependent upon temperature. So this voltage divided bias is not affected by temperature. It means no matter how much heated the transistor is, there won't be any significant impact on the transistor itself and the operating potential and operating capacity of it, which is very good point, right? So this is about some introduction of the voltage divided bias. Now, if you want to find out the expression of it, the voltage across R2. Let's find out the voltage across R2. What is the voltage across R2? So, voltage across R2. Now, if you see this voltage across R2, this would be V2 equals, yes, V2 equals equivalent resistance of these two. That means R2 by R1 plus R2 times VCC. Right. So this is what the voltage across resistance 2 is in the circuit. Now if you try to find out this VE, which is the voltage across ammeter, it would be V2 minus VBE. Because if you see here, V2, which is this one, that is the voltage across this resistance, V2, and this is VBE, and no, yes, VBE, this is VBE, and this is just VE. Now if you find out VE, if you want to find out VE, now this is the circuit. Now this VBE minus, minus. Okay. Let's use Kirchhoff's rule here, and if you do so, VBE equals minus VBE plus VE minus V2. So that's why the value for equals 0. So that's why if I want to find out this, then it will be V2 minus VBE equals VE. So this is what we get. Yes, this is which is same as this. So this is the expression of ammeter voltage across ammeter terminal in this kind of particular biasing. Now, if you find out the voltage of ammeter, then you can definitely find out the current across this, which is equals to given by, not RC, but rather RE. So this is what we get for the expression of IE. Now the collector current is approximately, here the collector current is approximately equal to the emitter current. So the collector emitter voltage would be VCE. Where is VCE? Now this is VCE. Now, yeah, so VCE would be what? Would be VCC minus ICRC minus ICRE, as a result of which VCC would be IC times VCE equals VCC minus ICRC plus IP. So this is what you get for the expression of VCE. Okay. Now similarly, you can find out the saturation IC To find out the saturation IC, what you do is you just set VCE equals 0, then you would get IC by this formula, which is this is equal to 0, so it would be minus of VCC by RC plus RE. In this way, you can find out the values of saturated current through collector as well as base. So this is it. I think it's a lot of mess here, but I think you get the point. So this is about the voltage biasing, voltage divider bias. Okay. This is something what we call as an emitter feedback bias, and the circuit of it looks like this. Now, what the word feedback here represent that whenever we have output that signals what to do to the input. So if the output suggests what to do in the input terminal, then that is what we call as a feedback circuit. And in this circuit, what happens is when beta increases in the circuit, then what it does is it increases this collector current, and this collector current is a result of increase in collector current. This Re is a feedback element in the circuit, and because of this feedback Re feedback element Re of the circuit, it suggests us to decrease this IB, which is base current. Now, if you want to find out the expression for VCE, then it looks like VCE equals VCC minus is this okay? I think it is. Now if you want to find out the VCE, it is equals to VCC minus ICRC minus IERE. Similarly, we know that this IE emitter current is nearly equals to collector current, and that's why what we can suggest is we can say equals VCC minus ICRC minus ICIA. That means we can write VCE equals VCC minus ICRC plus IE. As a result of which we can say IC equals VCE minus VCC by RCIE. This is what the expression of collector current is. Okay. Now, after this, if you want to find out the saturated collector current, what you do is you just set VCE equals 0, and that VCE equals 0, and in doing so, the expression so obtained is actually the saturated collector current. Okay. Now, what you know here is VCE cutoff is actually VCE, because if we say what is the cutoff, what is the cutoff value of VCE, then it is equals to VCC. To find out the value of VBE, yes, so if you want to express VCC in terms of this base this line here, then you would write something like, so you would what you do is you would apply Kirchhoff's law here, and it would be VCC equals IBRV plus VBE plus VE RE. So here, from here, what you can find out is the expression of, expression of, the expression of base current. And if you want to express the value of saturated base current, then you would have to consider VCE to be 0 or VCC equals 0. Wait, let me check. Oh, wait a second. Yes, the value of saturated current would be equal when this is equals to 0. No, this is not equals to 0. VCE equals 0. But since we do not have any VCE component here, we don't have to find out it, or even if we find out VBE saturated, then the expression is same as it is. So now this is what we get for the value of this. Now you can find out a lot of other values. For example, if you can find out the value of IC in terms of IB2, because we know the expression IC equals beta times IB. Now you can find out the value of IC in terms of this. So a lot of things you can do, but I'm not going to do that. So this is about the emitter feedback biasing.